Welcome back to Programming with Qt Widgets. Today is the day you've all been waiting for. Now finally, after 58 episodes of Programming with Qt Widgets, we get to the real hard part, namely tree models. We have list models, which are subclasses of QAbstract list model. They are one-dimensional. We got QAbstract table model, which are two-dimensional. And then we got the three-dimensional. No, that was not a spelling or pronunciation errors. I did not say three, I said tree, those that are in the forest. Because your trees are really not three-dimensional. They are only items under the first column in your trees. We'll get back to the significance of that a bit later on. The three-dimensional versions, you would think that they would be a subclass of QAbstract tree model, but they are a subclass of QAbstract item model. And that's what we're going to implement in the next episode. This episode, we'll talk about what we need to implement and understand what it is that we need to implement. Developing software with Qt is easy. You write it once, you deploy it everywhere. So the ad says at least. But sometimes there are tiny differences between different platforms. But fortunately, in KDAB, we have a vast amount of experience in that. We have people that can help you both on Windows and on Linux, and of course, Macintosh and embedded devices. So reach out to us if you have any of these kind of problems. So what we see here on the slide is all you need to do. And I love to say that, and I see the deer looking into the headlight faces on people in classes when I say that, and they've tried it themselves. But it isn't all that difficult. At least it's much easier now that we have been through all the building blocks for this. So first of all, you need to subclass from QAbstract item model. That is the most generic class of this, and it requires you to implement at least three methods. It needs you to implement column count and row count, and we saw those in the previous version. They took the parent here, and in the previous versions for the list, well, we didn't have column counts for list because that was just one. But for the table, the column count would take this model index, and we'd go to it and ask for row and column on the model index. But for now, we also might need to go and ask for the parent. For the column count, most of the time, it is just a number because you don't care about that you have different columns in your trees most of the time, sometimes at least. It's just the same amount of columns throughout the whole tree. So it could be as simple as return tree. This time it was the number 3. Then we have data. And data, of course, this time needs to both look at the row and the column and the parent, because the parent tells you where in the tree we currently are looking at. Optionally, header data, it's not really that optional because a tree usually have at the top of it, it has some headers. You only have the horizontal header on the tree, where in the table you also had the vertical one, but on the tree you only have the horizontal one, but you very often do have that. And then, that was the known land. In addition to that, you need to be able to create indexes. And so there's a method called index, and it takes a row and a column and the parent index, and you need to return an index for that. And for going up in the tree, at some point you might click somewhere in a tree and the tree view will be telling you, hey, you clicked on this item and now you would like to know something about that item, for example, where in the tree it is. And for that purpose, you need to implement parent for traversing up the tree. The hard part about these two methods is that you need to get them 100% corner case correct, otherwise your model is just crashing on you. So doing unit testing on these already from the start will sometimes both be useful for developing, but also for conceptually asking, so what should the index return when I ask for column 0, row 0, and the empty Q model index? Well, it should obviously return a Q model index, but that model index, what data should be available for that? But let's talk a bit more about the model indexes. There are two different kind of model indexes, conceptually at least. There is the model index representing the start of the recursion. It looks like this. It's a ball pen. And then there's the model index that represent somewhere in your tree, a valid item in your tree. This is those that we have here. See, these are valid. If I go and ask is valid, they will return true. This one is valid false. And why is it significant with these two different ones? Well, it's significant because at some point I need to start my whole rolling out of stuff. I need to answer row count for the very top at the tree. How many rows is at the top of the tree? And that is the top of the tree. I'm giving it the Q model index, parenthesis open, parenthesis close. This one here. How many rows do you have? Well, I have 22 rows. Okay, says the view. I would like to learn something about the first row. So to be able to learn something about the first row, it needs a model index, because knowing about the first row is asking data. Does it want to know what text is there? Well, data with a display role. So it needs an index. It cannot go with this one, because this index here, well, that represents above the tree. So what happens is that the view will go to the model and say, hey, given this model index being the parent, can you give me row 0, column 0, and this parent? And the model will say, sure, here is row 0, column 0. And now the view goes to the model and say, hey, can you give me data for the display row? Data for the display row with this particular index. Later on, at some point, it will likely also go and ask, dear model, what is the row count with this model index? And the row count of that model index will be returned. There is 10 children underneath this element in the tree that this model index represent. And the view will then say, okay, I would like to learn something about the first row, the first column, so row 0, column 0, underneath this model index. And Robert, can you please turn on some color here? Thank you very much. Oh, that's what I look like in color. Whew. Anyway, with this model index, the view goes and say, hey, dear model, can you give me an index for row 0, column 0, this model index? And it will return this one. Did you notice the color difference? For the view, they just look like this. You cannot tell, see, you cannot tell the difference between these two. Only the model really knows about the difference. And that will be significant when we talk about how do we create these indexes. Before we go and talk about this, let's just take one step back. I can see in your eyes that you're starting to get confused now. Why do we have all this Q model index and going and asking for a model index child of this one and getting this one and then this one and then this? Why? Well, remember, we would like to interrogate the tree deep down. So we did this already in a previous episode where I went like the first row, third child, the fourth of that, and can you give me the foreground color of column 7? For the first row, the fourth child, can you give me the foreground color or the background color and so on? And we realized, hey, a good thing would be to encapsulate this data somehow. Let's put a pointer, or let's represent it with a pointer. And then we had this discussion, what pointer? And we ended up, well, the only pointer we can do is a void pointer. So our tree, we have pointers, void pointers that we know what they really are and can cast them back to our real data structure. We have that encapsulated in here. And that's where These two are definitely you can see the difference even in black and white. These two are different to the model. The model know that inside of this void pointer, it can cast it to be a pointer to my real data structure. And this pointer will point to a different place than this one. So when I point this, I will get my satellite's data structure out of it. And if I ask for column number 8, it means the model year of that satellite. Yes, I'm just making it all up. And if I'm casting this one, well, column 3 on that one, it will be something else for another satellite. Different internal void pointers in these. That's exactly what the model index is. It's just a very convenient, but I admit, sometimes hard to get your head around abstraction for the void pointer inside. And why is that again? Well, we went over all of this already. It is type safety. If it was just a void pointer, anybody could create any void pointer and your model would crash deep down. So wrapping it inside a class is just an encapsulation that makes the whole thing much more type safe. Type safe, Jesper, what do you mean? Well, did you not watch the previous video where we were talking about the check underscore macros? Maybe you should pause this one and go back and watch that. Well, see, the key thing is that I can create this particular model index here. This one, my ball pen model index here, the one that sits above the tree. So on my tree view here, it sits up here representing above the tree. This one I can create. I will create it by saying Q model index, parenthesis open, parenthesis close. But I cannot create any of the others because the Q model index do not have a constructor for a model index for row and column and some internal data structure. For that, I can only, and that's why we need to go and ask the model all the time, only the model can create them. And how does the model create them? Well, my model subclasses from Q abstract item model, and in that superclass, there is a method called createIndex. It returns an index, and it's given either a row, a column, and an ID here, or a row and a column and a pointer. And that means that if I want to create an index, I can only do that either here, or I can go to the model and say, hey, can you get me an index? And the model says, absolutely, I can do that. And it calls up to the superclass, which creates the index. And inside of that index, it also has information about the model, which is why those check underscore that we saw in the previous episode, they can actually check whether that model index actually comes from me whenever I need to answer like data. Because if I was a model that only had 3 rows and you went to another model and say, hey, can you give me a model index for row number 22? And it had 22 rows, you would get a model index. But when you went to me with that model index, rather than trying to index into my internal data structure for row number 22, I would say, no. That index, none of mine. So what happens is that I call createIndex in my index method. I call createIndex to create the index, and it goes like this. Hey, dear model, can you give me an index? And I call createIndex, and I have some data structure. You can see my data structure here. This is a simple tree, and my tree has some items here. They are in the real world. I have some data structure that looks like this, but they all represent one-to-one a model index. Sometimes that model index doesn't, or that tree doesn't exist in reality, but is only made up on the fly. But sometimes, as we'll see at least in the next example, it does exist in reality. And the internal pointer here, this one here, that is what I'll put in. So you go to the model, you say, hey model, on this being the parent, that's the one sitting above here. Row 0, that would be this entry here. Column 0, that would be the first column in there. Can you give me an index for that? and I'll get an index for that. But just as I call createIndex, I need to give it a void pointer. So I take the pointer that is represented, this one here. I go and say, hey, what are you? Well, I'm 0x1234. Excellent. And that's what I put in there. And then I return the index to the view. And the view will see this. It doesn't know that I have my own secret data structure stored in there. And that's why the view can work with QModel indexes of any kind, because they all QModel index. Those that comes from our satellite model, those that comes from our file system model, those that comes from our thumbnail model, they all look like this. But to the model, and the model were the one creating the index. So the model will go as soon as it gets the data method, for example. Hey, can you give me the data? The model will go and say, oh yeah, I know that the index was created by me, and I know that I put a pointer in. So I go to the index. This is the index that I get from the view. Can you give me the data for this index here? And I just like, whew. And now I can open up my index. I can pull out a void pointer, and I know that it was my data structure, data node pointer. So I can cast it. I can do a static cast to that, because I know that nobody in the whole world besides me can create those indexes. That's the guarantee that I get from the QModel index constructor only being able to create this one, and everybody else needs to go through my superclasses createIndex, and therefore I'm guaranteed that I am the only one that can put that particular pointer in here. And when I go to the data or row count or column count or whatever, I can take my index and I can wrap it around, pull it out, and there we are. And that's it. There really is not much more to tell you about model view programming. There is QVariant. We learned about that long ago. That is how our data are returned here, so that we can return both the string and a pixmap and a whatever. We have QModel index, which wraps this internal pointer. We got these 4 methods for 5 methods, 1, 2, 3, 4, 5, plus very likely this 6th method to implement. And still, what is the matter with you people? Why don't you get it? Well, it is still when you sit there with your fingers on the keyboard and you say, I need to implement index. Ooh, index. Well, index, yes. So I got a parent, which is also an index, but my data structure is about my satellite data. How do I get from, well, don't fear. In the next episode, I will implement a model from scratch, and I'll go through the mental thinking about how do you do this, which hopefully will make it much easier for you when you implement your 22nd Qt abstract item model. For the 21st, you need to be thinking really careful and likely go back to the video. But now, please rewind to the beginning of this video and be ready to watch it one more time before you watch the next video, because I have been pulling together a lot of concepts, how the communication between the model and the view goes through these model indexes, and this particular is valid false, which, as I said in the previous episode, should really have been called is above the root. But anyway, until next time, have a great time.